And a quick word from one of our sponsors. This session is brought to you by GeoComfort. Help your clients live a zero energy and healthy lifestyle with GeoComfort geothermal systems, and featuring a renewed 30% tax credit for these geothermal or ground source heat pump systems. And our main sponsor today is Shrinergy. Shrinergy has mobile solar generators. These generators, the most powerful solar generator, yet still only weighs 20 pounds, capable of satisfying the demanding need for camp trailers, home appliances, days at a time. The generator is versatile as it is powerful for the ultimate emergency power or camping luxury without the hassle of traditional fuel power generators. This kit comes with all solar panel cables you need to get started, plus a wall charger, connected to the Solar Storm 100 panel, and fully recharge the solar generators within 15 hours of ideal sunlight. And here's some of the recharge times: 2 to 24 hours, wall plug 4 to 8, car 4 to 6. And then here is some of the times that certain devices take to recharge, with getting out of a full charge of a battery 33 hours on an 18 cubic Energy Star certified refrigerator. Shrinergy, with years of experience in renewable energy industry, has developed solar microgrid kits as well, with lithium-ion based battery storage for the U.S., Caribbean, Central, and South American markets. Based on highest quality PV panels and hybrid inverter technology that's available to the industry. Their kits provide rugged durability, long life, and reliable performance day in and day out to help keep electricity going for your clients. And also, if you're in Michigan, you can get paid to go solar. If you have anybody located in these particular utility areas that are in colors, reach out to Shrinergy today, as they are looking to develop solar sites and pay for that. All right, so this session we're going to be talking about sort of that question that comes up for everybody, whether they're doing a new build or a renovation or have an existing site, and that is, does solar work on my site? And that's a really big question to ask, and you might not know where to start. So we're going to be discussing an easy tool that was developed by NREL to really start that conversation in a less invasive way if you want to start exploring that for yourself or for your clients.
All right, now I'm going to try to switch over to my web browser and show you PVWatts live. So hopefully I can show you my screen. And so this is the PVWatts front page. And you'll notice there's our Getting Started box where we type an address. So I'm going to use the NREL street address. So you can type in a complete street address if you like. And then you type go. And then it just took that street address that's displayed up here and converted it to a latitude longitude value. This is the latitude and longitude of that square on the map representing the weather data. And the center of that square is about a half a mile from this street address. Now, normally you would see a map here that would show you that square and show you the address so you can see what I'm talking about. But unfortunately, NREL is having some licensing issues with Google, and so Google changed the terms of use for their mapping services. So we're working through those, and we'll come up with a solution here as fast as we can. So PVWatts still works. It's still converting street addresses to latitude and longitudes. It's still pulling weather data from the National Solar Radiation Database. It's just not displaying maps on the pages here. Okay, so once we've confirmed our latitude and longitude here, then we go to the system info page, and this is where you type, you provide information about your system design. And so I'm going to model a 6 kilowatt system. So this means that outside of PVWatts, I've decided that there's enough room on my roof for 6 kilowatts of PV modules. Maybe somebody gave me a quote and told me that, or maybe I did my own calculations. Again, when our mapping service agreement is back up, there's a little tool here that you can use to draw a picture of the the array on your roof that will help you come up with this estimate. But there are quick ways to do that, sort of back of the envelope estimates that you can use. So anyway, this is the size of the system in DC kilowatts. And we can choose module types. So either a standard module would be sort of a common crystalline silicon, either mono or polycrystalline cells. A premium module would be one that a crystalline module with higher efficiency. And then a thin film module would be for thin film. And if you have questions about these parameters, just click the little I next to the input there. And here's a description for the module type input with some details about what those 3 module types represent in the model. I'm going to model a roof mounted array. So the difference between a fixed open rack and a fixed roof mount. So fixed array means it doesn't move, it's not on a tracking system. And then an open rack setup means that air can flow behind the modules and cool it off. So remember I showed you that the weather data that PVWatts uses includes the wind speed. And that's because the model takes into account the effect of wind blowing across the modules, the cooling effect. So a roof mount system is going to have less air or no air moving behind the module, so it's going to run a little hotter than an open rack module. And we have options for tracking as well. And again, for details about those, you can look at the sorry, I clicked the wrong I there. At the input. So here's a diagram of the different tracking types with some descriptions.
So Paul, would it be accurate to say that a majority of projects are going to be selecting that fixed open, or not open rack, but the fixed roof mount?
Yeah, if you're modeling a rooftop system, a residential rooftop system, or a commercial, if you've got well, it depends. For some large commercial buildings, you know, the modules may be mounted, you know, high above the roof surface. But for most residential and commercial applications, you're talking about a roof mount. The open rack would be for a ground-mounted system, and then of course the one-axis and two-axis tracking options would be generally for large ground-mounted arrays. I'll just make a quick note about the one-axis tracking option also accounts for self-shading. So the one-axis tracking array type assumes that you've got rows of modules and that they're rotating on a tracker. And if those rows are too close together, then in the early morning and late evening, you're going to get shadows on the modules. The modules are going to shade each other. That's called self-shading. And if you move the rows apart, then there'll be less or no shading. You can eliminate the shading completely by moving them apart. So that's accounted for in the one-axis tracking options.
Paul, I know there are certain solar panel types that, if there is shading, can still function. Is that what you would select for that, even on the roof, or what would you be using for that?
Yeah, so I mean, so PVWatts is designed to be real simple and not get into sort of a lot of details of different design types. But if you've got a design that you know, responds to shading differently than sort of a standard crystalline silicon module would, then you can, if you're confident that it's, you know, if you've got a one-axis tracking array and you've got some sort of system that's supposed to deal with shading and you're confident that shading is not going to affect the output of the array, then you could set it up as one-axis tracking and then make the rows very far apart so that there's no shading. That would be how you could handle that situation.
But it would still have to be a tracking solar array, right?
Yes, if you're if you're modeling an array that has tracking, you want to model tracking because that gives you quite a significant boost compared to a fixed array
right.
in terms of total output.
So it wouldn't work with a fixed array that has the special inverters that still work with the shading, correct?
Right. So for PVWatts, the fixed options do not account for self-shading. The self-shading is only accounted for with one axis. So here we're basically assuming that for a roof mount system, the arrays are all in the same plane, so there's no self-shading.
Thank you.
Mm-hmm. Okay, and then for the system losses, I discussed that a little bit in the step-by-step. If you want a description of how the losses are calculated and what the default values are, we've got that in help, and then we have a loss calculator here. So you can use this to calculate your 14%. So if you had microinverters, for example, and wanted to set the mismatch loss to 0, then you would set that to 0. But then you've got some additional loss due to conversion efficiency in the electronics. So you might want to increase another loss category by 1% or something. So you can make adjustments here, and then it calculates a new system loss value for you. Or you can just type a new number here. For example, I could just get rid of that 0.8 and make it 14%. And then the tilt angle, so that's the tilt from horizontal. So if your modules were parallel to the ground, you'd have a tilt angle of 0. We've got a little table in help here that converts roof pitch to tilt angle. For those of you who are building designers and more comfortable with roof pitch, so I'll go ahead and change mine to 18 degrees. And then the azimuth angle is the orientation with respect to the equator. So 180 azimuth angle means that the array is facing the equator, so that it's tilted up toward the equator. If you had an azimuth angle of 0, it would be tilted toward the North Pole, and which would be appropriate if you're in the southern hemisphere. You'd want to change this to 0. And again, we've got a table here converting different compass headings to azimuth angles. And you can specify values in between here, so you can have 30 degrees or 46 or whatever. Okay, and then here's our our retail electricity rates. You can switch it from residential to commercial, and that just pulls the default rate from that database I discussed before. So I'll come back to the advanced parameters. We'll go ahead and go to the results page. And here are the results. So the total annual output is estimated at about 8,800 kilowatt hours per year. Again, these are AC kilowatt hours. Here's the monthly breakdown. This is the solar radiation data from the weather file, and it's given in kilowatt hours per square meter per day. So you can think of these as sun hours per day. So this means that in January, we have about 3.7 hours of full sun per day. And of course, it goes up in the summer, and the peak month is June. And then you have a summary of your inputs down at the bottom of the page. This page is has all of the information, the inputs and the outputs from your run. You can send this to your printer or to PDF. If you do that, you can type some notes here. Type some notes there, and then click print here. And I'm going to send this to PDF. And there's the PDF that is generated. So if that's useful for you, you can use that. Sorry, it looks like I just closed out of there, but that's fine. We'll just go back here. You can also generate text files of the data. So if you want to look at monthly data, for example, this generates a CSV file. So this has a summary of all the inputs. I just opened that CSV file in Excel. And then there's the monthly data. If you're interested in looking in detail at the hour-by-hour data, you can download the hourly CSV file. There again, we have a summary of the inputs, and then there's the hour-by-hour data. So you've got the beam and diffuse irradiance from the weather file, the temperature, wind speed. That's all inputs from the weather data. And then the plane of array irradiance, that's the solar energy incident on the array. The cell temperature, the DC array output, the AC output. So all that information is there if you're interested in more detailed look at what the model calculated. There's also here, if you look carefully under the total annual output, there's a range here. So this is a model, and it's estimating these annual output values, and the monthly output values are estimates based on the model's calculations. So this here kind of gives you a sense of what a reasonable range of values is to expect based on these results. And there's a little more discussion of where these numbers came from in this window that pops up if you click here. So if you're interested in how to think about the accuracy of the model, this is a useful little tool. So let's go back for a minute to the system info and just look at these advanced parameters that I skipped over. So the advanced parameters are hidden by default. You can expand them by clicking the plus button. We have a DC to AC size ratio, inverter efficiency, and ground coverage ratio. I'll start with the ground coverage ratio because we were talking about shading earlier. So it only applies if you choose a one-axis tracking option. And the ground coverage ratio is basically a measure of the distance between rows of modules, and it's defined as the area, the module area, the total module area of the array, divided by the area of the ground occupied by the array under the modules. And there's a more detailed definition in help. So a smaller ground coverage ratio means that the rows are further apart than a larger one. The DC to AC size ratio, this comes into play if you're doing optimization where you're oversizing the array. So you might, relative to the inverter. So in order to save costs, you might decide to use a smaller inverter than you need to convert the array output at its peak power, because the array is only going to operate at its peak output for a short time of the year. So you might not want to have an inverter sized for that peak output. You could save money by using a smaller inverter and having it run closer to its rated capacity most of the time. And then for those few hours when the array operates at its peak, then you just adjust the array output downward. You reduce the power output, and that's called clipping, inverter power clipping, where the inverter reduces the array power output to avoid damaging itself. So the DC to AC size ratio is the DC capacity of the array in kilowatts divided by the AC capacity of the inverter in AC kilowatts. So the larger the DC to AC ratio, the larger the array is relative to the inverter. So you can account for that sizing optimization problem in PVWatts. And then the inverter efficiency, this is the DC to AC conversion efficiency of the inverter. And it's 96%. This is the peak conversion efficiency, so the nominal output of the inverter divided by the nominal input of the inverter. It's not the CEC weighted efficiency or the European weighted efficiency, it's the peak efficiency. Again, as with all these other inputs, if you're not familiar with them or you don't have a reason to change them, you can just go with the defaults. But the inverter efficiency is an input that you can adjust. I'll show you around some other parts of the website here. If you click Help, that shows you the sort of documentation that I was showing you before. It also provides some other links. One is to this technical reference. So this is we have a short technical description of how PVWatts works written up here, and then a link to an NREL publication that's a more detailed description of the algorithms behind the model. We also have some additional tools for developers. I'll show you these in more detail, but there are links right here from Help. And then some details about different releases of PVWatts. Legal disclaimer: if you're using PVWatts for business purposes and need legal language for that, you can find that here in the legal disclaimer. And then you can get in touch with us by clicking the feedback button here. That's an email address that you can use to contact us. And if you're new to PVWatts, there is a Getting Started section here that you can read over, which basically goes through what I just did. There's also a link here to a list of other NREL solar tools, and PVWatts is the one we're talking about now, and SAM is another one that I'll discuss a little bit more here later. But there are a number of other tools available, and this is kind of a launching point to go explore some of those. All right, so are there any questions about my demo before I move on to the next segment?
Paul, could you, has there been any studies or plan to be of where folks who go in and use PVWatts, just novices, to do projected assessments and then actually install the systems to see how accurate the projections were versus what actually happened?
Yeah, there are some NREL publications, we call them validation studies, where we've taken PVWatts and SAM, PVSYST, PVSOL, some of the PV modeling software out there, and we've taken a real system where we have measured data, and then compared that measured data to the outputs of the different models. So that data is out there, or those studies are out there to read. And what I can say is, in general, you know, the quality of your results is only as good as the quality of your inputs. So generally, for those kinds of validation studies, it takes a lot of work to kind of make sure that the model is actually representing the physical system as it is, and so it takes sort of adjusting inputs of the different models to account for things like, you know, there was an outage in the actual system that the models are not accounting for, so we have to make adjustments to the inputs to account for that, and so it's tricky trying to represent real life with a computer model. But yes, there are studies that you can read. They're short little papers. If you're interested in those.
Okay. The next question was, and I think this is what the question is asking, and it's definitely I was definitely taken off guard here to see your drawing system down, because honestly, I think when we use this tool, we've been using it for several years. It's actually one of the #1, personally, I feel like it's one of the #1 values of this tool, is that you can go in and do kind of a site assessment on an existing building or on a planned development, or, you know, an array, a ground mount if you want to draw it out. So do you have, maybe here in your PowerPoint, maybe you've captured some of those in visuals that we can see that? Do you have that coming up?
I don't have those. I put this thing together after the site was down. I could probably dig around and find some, but I'm not sure it's worth taking everyone's time to do that.
Sure.
But
I
yes.
I guess I was going to say, you know, maybe you can try to talk us through that, because I didn't want to discount that too much, because, you know, I think it does make a huge impact to be able to do that.
Yeah, let's see. Yeah, I'm just looking to see if I can quickly find some. Mapping isn't working, but basically what it does, and I can take you to the NSRDB website to show you the maps on which PVWatts is based, and like the NSRDB website's not working. So we've been having problems with the website at NREL. So we're doing our best to deal with those. Here, yeah, it's obviously not working perfectly. So I'm going to have to explain to you what happens here when everything's working correctly. So like I said, normally there's a map that appears down here, and it's a Google map. So it's a Google map of, you know, with a pin where your address is, the address that you typed. And then overlaid on that map are these colored rectangles indicating the weather files that are available for each 4 kilometer square. And then one of those rectangles, or one of those squares, is highlighted in blue, and it's superimposed over your pin, over the address that you entered. And so that square represents the weather file that's being used for your analysis. And then you can just go ahead and use that default weather file, which is this one here, or you can click on the map to move that blue rectangle to use, like you could go to the grid cell, to the 4 kilometer square cell right next to the blue rectangle, to use a weather file for, you know, that's nearby. Sometimes that's a useful technique if you want to kind of get a sense of how the solar resource might vary within your neighborhood, say. So the map tool is useful for both verifying the weather data that you'll be using, and also for choosing other weather data. And then it also has a tool for choosing legacy data. So I mentioned that the original PVWatts version used an older TMY2 data set, and the map tool actually allows you to choose that older file. So if you've been using PVWatts for a long time and want to compare results between the new weather data set and those older data sets, you can do that. And it just occurred to me that I think there's a picture here, yeah, in the help. So this is what you would normally see, is this pin indicating the address that you typed, and then the rectangle representing the weather file. And then that distance, the 0.7 miles, is the distance between this pin and the center of the rectangle. And then you can choose to display legacy data options by checking these boxes. So if I check this box, then I would see the TMY2 pin, for example.
Now, I do know if you zoom in, you'll actually see, like a Google Earth, you'll see the structure. correct, and you can kind of measure it, and then it gives you back your estimated. I mean, I think that's the biggest question people have is, how many kilowatts can fit on this kind of like this picture you have here, but it's actually of the structure, correct? And a lot of people just really don't know how much can actually fit there. Would that be correct to say?
Okay, yeah, that's right. So on the system info page, again, normally there's a little map here, and that's zoomed in to right above the address, so you can see the building features. You can see the roof, and then you can draw a little shape over the roof, and then it estimates the area of that shape, and then based on that area calculates system size. And it's a real rough estimate, but if you've got nothing else, it's a reasonable start. So that is a useful tool that you can use to, if you're just getting started and want a rough estimate. One of the problems with that technique is that it doesn't actually account for the roof slope. So it's drawing a flat rectangle on top of a picture of a sloped roof. So there's that estimate tends to be, it's better than nothing, but it's not completely accurate either.
Isn't I mean, if you've got a sloped roof, you would probably actually have more square footage, and then once you use the tilt here, depending on your roof pitch. That's
right. Yeah. So you would draw your rectangle over that picture of the slanted roof, and then maybe adjust the system size upward a little bit to account for the additional area, and then you want to make sure that the tilt angle represents the roof pitch.
Okay. Well, yeah. Hey. Well, thanks for helping talk us through that, and I think all of you, when you come back and see it back up and running, you'll go, oh, I see what to do here. It's pretty straightforward. But so the next question is, so am I correct that the self-shading model does not account for backtracking?
So we have two options for one-axis tracking. One is one-axis tracking without backtracking, and the other is one-axis tracking with backtracking. So you can do either. So the backtracking option means, so I'll just back up for a second. So one-axis tracking means that the modules in the array rotate about an axis, generally from east to west, and they follow the motion of the sun throughout the day. So the array is always pointing toward the sun. So it's just moving in one direction. So two-axis tracking would mean that it's moving, following the movement of the sun throughout the day, and also follows the movement of the sun throughout the year for different seasons. So it's tilting up and down and rotating. One-axis tracking means it's only rotating. And then for backtracking, that's kind of a more sophisticated tracking algorithm. Then what happens is as the modules are rotating, if the front row is shading the row behind it, then the row behind it rotates a little bit to get out of the shade. So then it's not pointing directly at the sun, but it's not shaded. And then the front row stays pointed at the sun. So that's basically what backtracking is. So you can model one-axis tracking with or without backtracking. So backtracking essentially eliminates self-shading. Any other questions about this? Before
Great. That actually answered two questions in one. Thanks. Is there a way to simulate building integrated PV? That's BIPV. If you've got it on the facade.
Well, you can. I mean, you can. So you could. There are a couple of features. If it's mounted, sometimes BIPV is mounted horizontally on a wall. So you might you could just do that by changing the tilt angle to 90 degrees, and then changing the azimuth angle to whatever the orientation of the wall is. And then you would want to change the module type, the array type to fixed roof mount, with just so you're accounting for the fact that the back of the module is not exposed to the wind. But a more sophisticated model, I mean, in some cases, if you've got PV modules that are functioning as windows, then the module is interacting with the indoor air, and the indoor air temperature is affecting the performance of the module, and that we're not modeling here. So you can get at part of the BIPV a building integrated module, but not in a whole lot of detail.
And the last one before we move on here, if the service provider has tiered rates based on kWh used, which I'm assuming means like in where we're at, if we go over 600 kilowatt hours in a month, we get charged a different fee. Does PVWatts average or just use the lowest?
So PVWatts, the web version of PVWatts doesn't account for that at all. So it's just using this flat rate. It just assumes that all of the power generated by the PV system is compensated at 11.1 cents per kilowatt hour. So it doesn't account for time of use rates. It doesn't account for times when the PV system generates more power than the building consumes. If you want to look at those questions, then you should use SAM. SAM has a great detailed electricity rate calculator that looks at, it downloads rate structures from a database. It accounts for time of use rates, tiered rates, demand charges. It also accounts for the building electric load, the electric consumption of the building. So if you've got excess generation, you can account for that. And it does net metering or feed-in tariffs or different types of compensation for excess generation. So if those are the kinds of questions that you're asking, go to SAM. You can still use the PVWatts performance model, but then you get to use SAM's more sophisticated electricity rate calculator.